Hello, class. Welcome to part two of our discussion on section 5-7, designed for cyclic loading. Right now, we're going to look at brittle materials. So, brittle materials in the past have generally not been considered viable candidates for cyclic loading, but it's becoming more and more acceptable to look at them. However, due to the nature of brittle materials, you have to add stress concentration factors into the mix and consider the flaws and the cracks and crack tip propagation and all of that stuff as you look at brittle materials as a cyclically loaded material. So previously we looked at ductile materials, which we had this nice plot of mean stresses and alternate stresses. We had our yield line, we had our Soderberg criterion, we had our Goodman criterion, we had our early cycle loading check, and our Gerber criterion. So with brittle materials, the thought is that you should consider your stress concentrations in both the alternating and the mean stress considerations when you evaluate these criterion. So if we look at it, we're not going to look at the Soderberg criterion because it's considering the mean stress versus the yield strength, which brittle materials generally look at the ultimate strength. So we're going to go into our green, and we're going to look at our Goodman. If my pen will work. There it goes. Our Goodman criterion. And what we can do is we can modify it to look something like this. So we have originally we had our, oh, come on now. There it goes. We had our stress concentration as it applied to our alternating stress divided by our estimated actual endurance limit, plus our mean stress as it considered our ultimate strength compared to our ultimate strength, and that was over our design factor. So in this case, now we're going to add a stress concentration factor into our consideration of our mean stress, and that will help look at the crack tips and the crack tip propagation and make sure that we're still maintaining our safety with a brittle material instead of a ductile material. Similarly, with our early cycle loading check here, instead of using yield strength, we'll use ultimate strength. If I can get this to work. Right, so early cycle. Oh my goodness, this cracked screen is really giving me some trouble right here. Come on, pen. There it goes. We can look at our early cycle, and I'll call it failure in this case. And we can look at our stress concentration times our alternating stress over our ultimate strength plus our stress concentration times our mean stress over our ultimate strength, and that's equal to 1 over n. Now, these equations aren't necessarily listed in your book, but we can extrapolate based on what we're trying to do that our stress concentration will add into our mean stress calculations. So if we go in here and we'll change colors to orange, we can look at our Gerber criterion again. Now again, we're going to add in our stress concentration factors. Come on now. There it goes. Gerber criterion. We're going to add in our stress concentration factors to our mean stress calculations. So right here, we're going to add this in. Times n times sigma m over ultimate strength, quantity squared is equal to 1. Right? So that's our brittle materials discussion in a nutshell. We're just going to add in our stress concentration factors into our mean stress considerations. That's it. Pretty simple, pretty straightforward. Just want to make sure that we're maintaining a safe design when we use brittle materials. So what we're going to move on and look at now is a consideration for multidimensional loading. So in our previous discussion, when we looked at all of these considerations, we've had perhaps a stress element that looked something like this, and we had sigma max applied here, and then we had the same element in stress state number 2 with a sigma min looking something like this. So it's one-dimensional loading. So what we're going to consider now is multidimensional loading. So if we have a stress element and it has the generic shape, if my pen will draw, there it goes, something like this, where it has multidimensional loading. And it may have some or all of these. So I'll say sigma x max, and I'll say sigma y max, and I'll say tau xy max, like that. Now straight stress state 1, and then if we look at a second stress state, perhaps it has something like this, where this is sigma x min, sigma y min, and the same sort of thing, tau xy min, in whichever direction or orientation that the stress is in. So this is multidimensional loading, right? So this makes things a little bit more complicated. Not impossible to calculate, but just a little bit more complicated. So we're going to break it down into two parts. We're going to look at our mean stresses separate from our alternating stresses. All right. So if we look at our mean stresses, come on now. There it goes. All right. So if we look at our mean stress here, we can say that our mean stress, again, is sigma max plus sigma min divided by 2, right? Or maybe our tau mean is equal to tau max plus tau min divided by 2. So what we're going to do is we're going to draw some more circles, right? So we'll have a, oh my goodness, this pen is just driving me nuts. Here we go. So we'll have a sigma mean in the x direction, and we'll have a sigma mean in the y direction, and then we'll have a tau mean in the xy plane. So what we'll do is we'll draw some more circles, more circles. Yay, dad jokes, right? So we can have maybe a point here and maybe a point here, and I'm just drawing points arbitrarily because it doesn't necessarily matter, and then I'll draw a Mohr's circle around like that. And then similarly to our previous Mohr's circles discussions, we will have our interior circles to that, or perhaps they're exterior circles. It'll depend on your loading conditions. Again, this is multidimensional loading, but we'll have a sigma 1 for our principal stress, a sigma 2 for our second, and a sigma 3 for our third principal stress. All right. So we've taken our mean stresses and we've turned them into another Mohr's circle, like so, or Mohr's circles. So based on our previous discussions in Chapter 4 of our von Mises and our Tresca stresses, again, come on, pen. Our Tresca stress, or our maximum shear stress theory, says that our sigma prime is equal to sigma 1 minus sigma 3 divided by 2. Okay, so what we're going to do is we're going to take this equation, we're going to say that our sigma mean prime, because we're looking only at our mean stresses currently, is equal to sigma 1 minus sigma 3 divided by 2, right? Now, alternatively, right, so you pick one or the other. You pick either your maximum shear stress theory, which is this guy, or you pick your distortion energy theory, which get my pen to work a little bit better. Distortion energy theory, which is also our von Mises, right? Sigma E is based on all of these principal stresses equal to sigma 1 minus sigma 2 quantity squared plus sigma 2 minus sigma 3 quantity squared plus sigma 3 minus sigma 1 quantity squared. All of this divided by 2. And the entire quantity of this square rooted. Okay? So what we're going to say is that our sigma mean prime is equal to sigma E, right? Which is equal to this equation up here, which I don't feel like rewriting. in the interest of time. So you're going to pick one or the other, maximum shear stress theory or distortion energy theory, and you're going to find a sigma mean prime, right? So instead of our previous sigma mean, we're going to use sigma mean prime, right? Now, we're going to do the same thing for our alternating stress. Recall that the equation for alternating stress is sigma A is equal to sigma max minus sigma min divided by 2. Similarly, our tau alternating might be, oops, not a sigma, but a tau max minus a tau min divided by 2. And again, we'll draw more circles based on, come on now, based on our alternating stresses. So we'll have something like a sigma x alternating, or sigma alternating x. Perhaps I'll try to stay consistent. And sigma alternating y, and then we'll have a tau alternating xy. And we can draw points here and perhaps a point here. And we can draw a circle there and maybe a circle there and another circle there, right? So now using the same maximum shear stress theory and distortion energy theory, or Tresca and von Mises respectively, we can say that our sigma, come on, I'll write it here, our sigma alternating prime is either equal to sigma 1 minus sigma 3 divided by 2, or our sigma alternating prime is equal to sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 quantity squared plus sigma 3 minus sigma 1 quantity squared divided by 2 square root. Pick one or the other, right, where these are sigma 1, sigma 2, and sigma 3, right? So what we've done is we've drawn two separate Mohr circles, one for mean stresses and one for alternating stresses, and we found our sigma mean prime and our sigma alternating prime. And then we take those, and now we're going to apply them into the same equations that we used before, right? So now we're going to go in here and we'll go draw, and we'll go blue, and we'll say Soderberg criterion. Again, this is for ductile materials, or works better for ductile materials. And we'll say our stress concentration factor times our sigma alternating prime, which is based on our multi-dimensional loading, divided by our estimated actual endurance limit, which does not matter, or does not factor a change with our multi-dimensional loading, plus our sigma mean prime based on our multi-dimensional loading over our sigma yield, which again is a material property, is equal to 1 over n. And this is equation 5-31 in your text. Right? Now if we go in here, we go into our green, we can go into our Goodman criterion. And this will look similar, and we'll say that our stress concentration factor, oh, this cracked screen is going to make me crack the screen even more when I throw it against the wall. Stress concentration factor, KT, times sigma alternating prime divided by our estimated actual endurance limit plus our sigma mean prime over our sigma ultimate, right? Or our ultimate strength is equal to 1 over n. This is equation 5-32 in your textbook. All right. Similarly, we can check for our early cycle yielding with equation 5-34. Right. Yes, I did skip 5-33, but that's okay. I'll get it here in just a second. And this is going to look like our stress concentration factor times our alternating stress prime over our yield strength plus our stress concentration factor times our mean stress prime over our yield strength is equal to 1 over n. Again, this is early cycle. Okay, do it nice or do it twice. Ugh. Cycle yielding, like so. All right, now let's look at our color orange, and let's look at our Gerber criterion, which again is going to be based on our alternating stress prime. So we have stress concentration factor, design factor, alternating stress prime divided by our estimated actual endurance limit, plus quantity, design factor, times sigma mean prime divided by our ultimate strength, quantity squared, is equal to 1. And this is equation 5-33 in your textbook. All right. Again, in our discussion on cyclic loading, design for cyclic loading, we're going to skip the Smith diagram, which is still a valuable tool. However, we're just not going to focus on it for the course material here. So this is going to conclude our discussion on design for cyclic loading, focusing primarily on ductile materials. However, we do have some considerations for our brittle materials. And then we look at multidimensional loading, which we want to consider when we have different stress elements, different loading on our stress elements, and we combine them with our mean stresses and our alternating stresses in two separate Mohr circles, and we have something that resembles these final equations. So I'll have these videos posted up, and I'll have these notes posted up for you guys to follow along with here shortly, and then we'll continue our discussion with Chapter 6, our design for columns.